All right, hello everybody. We are looking at, trying to get my pen to work. We are looking at chapter 20 in the statistics modeling our world curriculum here. And this is a focus on hypothesis tests for proportions. And it's the third chapter in inference. We've talked about sampling distributions and we've talked about confidence intervals. We're now looking at sort of the last section of what we typically look at in AP statistics for an inference test for proportions. And so this hypothesis test is it's very similar to that of a confidence interval. A confidence interval in general gives you a plausible interval of values. A plausible interval of values. So we have some population. We look at the sample that we got, and based on the sample that we have an interval of plausible values. These are values that, with a certain level of confidence, we can be sure that that population proportion is inside of. Now, a hypothesis test is a little bit different. It's kind of a twist, but it uses the same calculations, and thus the information that we learn from a confidence interval is related to what we're going to be doing with a hypothesis test. And a hypothesis test, the point of it is to determine a probability, right? It's to determine a probability that an event will happen, or our observed data will happen, given that a certain event, that we know that this thing to be true. Okay, and we'll talk about that more as we go on. Let's kind of like start from the beginning here and talk about hypothesis. A hypothesis is a working model that we adopt temporarily. Okay, we start by looking at a hypothesis to see if it's a model that makes sense. Okay, this starting hypothesis is called the null hypothesis, and we usually denote that as H sub 0, right? H sub 0, and which I of course wrote right there also. The null hypothesis specifies a population model parameter of interest and proposes a value for that model. So, for example, we might see something that says like the null hypothesis is that p equals 0.3, which is saying let's give it some context here. Let's talk about M&Ms, right? We might say that 30% of M&Ms are blue. Okay, that's my null hypothesis. 30% of M&Ms are blue. And like it says right here, when we're dealing with the null hypothesis, we always write it in this kind of form. Whatever the parameter is, in this case p for our population proportion, we use the equal to sign, and then whatever the hypothesized value is, in this case we wrote 0.3. So my null hypothesis is a starting working model. I'm adopting it temporarily. 30% of M&Ms are blue. Okay. Now the alternative hypothesis, which we denote as H sub A, contains the values of the parameter that we consider plausible if we reject the null hypothesis. And when I say reject the null hypothesis, what I mean is we are going to say that this is not true. Okay, this is not true. We're going to test that, and the alternative hypothesis would be that the actual proportion of blue M&Ms is smaller than 0.3. So we're going to make an assumption that it is 0.3, and then we're going to sort of test, assuming that this is true, what makes sense. Okay. And we're going to test really to see if that alternative hypothesis is smaller than that. So the null hypothesis specifies a population model parameter of interest, proposes a value for it. Again, that's like we might say that it might be 0.2. We want to compare our data to what we would expect if this was true. So the observed amount that we're going to do, we're going to compare it to assuming, working under the assumption that the null hypothesis is true. And we do that by finding how many standard deviations away from the proposed value we are. So just like we did with the confidence interval, we're going to look at a sampling distribution, and we're going to say, assuming that this actually is 0.2, let's say my observed value was 0.16, we want to know just how many standard deviations away is 0.16. And if it's low enough that we consider that, we then ask ourselves how likely it's going to be. And if it's a really unlikely occurrence that 0.16 would happen if this were true, then we determine the results of what our hypothesis would be. We either reject the hypothesis or we fail to reject the hypothesis. Again, we'll talk about that in more detail as we do some examples later in the video. The logic behind this is the same kind of logic that we use for juries. Okay, like in a trial of law. To prove someone is guilty, we start by assuming they're innocent. Our entire legal system is built on the idea that people are innocent until proven guilty. We have a null hypothesis that everybody who goes to trial is innocent. Okay? We retain that hypothesis until the facts make it unlikely beyond a reasonable doubt that it is not true. We continue to believe that they are innocent until we can prove beyond a reasonable doubt that it is not true. Okay? Then and only then do we reject that hypothesis, right, of innocence and declare the person guilty, right? We only say a person is guilty unless we have proven beyond a reasonable doubt that they are guilty. If we can't do that, we assume they are innocent. And this is one of the reasons why a lot of trials tend to not convict people where people really think that they did, but because the proof doesn't lie there, we assume that they're innocent, right? It's not that they necessarily were, it's just that we weren't able to develop enough facts to prove beyond a reasonable doubt that they are guilty. We have the same logic on a hypothesis test, okay? We are saying that H sub 0, the null hypothesis, we are assuming this to be true. And we're going to continue to assume that it's true until we can prove beyond a reasonable doubt, right? So we assume this is true. We consider whether the data is consistent with that, right? Does it align with this being true? And if they are, we retain that hypothesis. We don't change it. But if they're not, we have to ask ourselves whether the evidence that we have found is beyond a reasonable doubt. And in a hypothesis test, we can quantify that level of doubt, right? We can quantify that level of doubt with this thing called a p-value. And a p-value is a statistic that we're going to calculate, right? We use the model proposed by the hypothesis to calculate the probability that the event we've witnessed could happen. So the p-value is a probability. It's given that this is true, given that our null hypothesis is true, what is the probability that, and then I'm just going to like point an arrow down here so I don't know that. What's the probability that the event we've witnessed could happen? So we are going to calculate this level of doubt by saying, what's the probability that given that the null hypothesis is true, what's the probability that the event we've witnessed could happen? Okay? And that p-value quantifies exactly how surprised we are to see our results. it tells us just how rare of an event it is, and that's called a p-value. When it's consistent with the model, the p-value is a high number, right? Remember, it's a probability. So when the probability of an event happening is like 0.78, right? That's a pretty high number. And because that's a high number, we don't reject the null hypothesis. We retain the hypothesis because our results are consistent with that. However, we retain, that's what we were saying there. However, when it's low enough, actually, before I say that, let's say this, right? Since we can't claim to have proved it, instead we say we fail to reject it when it's not consistent. Okay. Typically speaking, we don't say we don't say that the null hypothesis is true. We just say we don't have enough evidence to reject it, right? We don't say that it is true. We just can't prove that it's not true. Okay. The p-value, the event happening, given that that's true, is fairly high. Okay. The little bits of difference that we see could be from natural sampling variability. However, if the p-value is low enough, we reject the null hypothesis. And rejecting the null hypothesis means I don't believe that the null hypothesis is true. And my observations and my data is consistent with that. So I reject the null hypothesis in favor of the alternative hypothesis. And typically speaking, a general level of how do I know when to reject it is when my p-value is below 0.05. We have some things that will change that in different thresholds, and we'll go into those things at a different date. But for right now, you can kind of just think in your head, if my p-value is smaller than 0.05, then I'm going to reject it. If there's less than a 5% chance that this observed amount could happen, given that my null hypothesis is true, I'm going to reject it. So that's what we're calculating when it comes to a p-value, okay? So let's actually do the 4 parts. And I'm actually going to pause right here. We're going to call that the end of this video, and the beginning of the next video is going to go over the 4 basic parts of the hypothesis test. So thank you for watching. Bye.